development sponsored by AICTE Academy. Professor, so Dr. Ranjan Kumar Behra sir is with us. Sir is going to deliver expert lecture on planning and design of smart microgrid with switched network system. Welcome, sir. Let me introduce about Ranjan Kumar Behra, sir. So Dr. Ranjan Kumar Behra received the Bachelor of Engineering degree in Electrical Engineering from the Regional Engineering College, now NIT, Rourkela, and MTech and PhD degrees from Indian Institute of Technology, Kanpur, India in 1998, 2003, and 2009, respectively. He worked at Hindustan Aeronautic Limited, Sonabeda, as a trainee engineer since May 2009. He is a faculty member in the Department of Electrical Engineering at IIT Patna, where he became head of the department in January 2016 to 31st March 2019. During July 2008 to February 2009, he was a visiting scholar in the Energy System Research Center, Tennessee Technological University, USA, and also as a visiting research collaborator at ECE Department, University of Pretoria, South Africa, during July 2016. He got several national and international awards such as Young Scientist Award in Engineering Sciences from DST, Government of India 2001. Selected as the Featured Engineer of the Globe 2015, USA, and Bhaskara Advanced Solar Energy Award, Indo-US Science and Technology Forum 2014 for doing solar research in Energy System Research Center, Tennessee Technological University, USA. He published more than 1 or 2 research articles in different national, international journals and conference proceedings. His current research interests include power electronics, high power motor drives, smart grid, and IoT applications. He is co-authored a book entitled Power Electronics, Drives and Advanced Applications, CRC Press, April 17, 2020. So on behalf of Electrical Engineering Department, Rajakiya Engineering College, Sonbad, I am welcoming you, sir. I am requesting you, sir, please share your screen, sir.
Okay. Thank you, sir. Thank you so much. This is, I think, last year I gave a lecture on IoT.
Yes, yes.
And this year I want to give a lecture on planning and design of microgrid. So thank you very much. And I'm just sharing my screen. So is it visible now?
Yes, sir, visible, sir.
Just I'm putting, it is a full screen mode. Is it working?
No, sir, now it is not in a full screen mode.
Okay. Oh, sorry. Yeah, I think I'll put the PDF version. Maybe that will work.
Okay, sir. Yes,
Is
sir.
it coming?
Yes, sir. Yes, sir. Full screen mode, sir.
Oh, okay. So actually, in this computer, I don't know, this Google Meet is not working. All other things are working fine.
Okay, sir. Yes.
Okay. Thank you, sir, for introducing me. Although I am not in that qualified, but I am also a student along with all of you. So I give lecture and learn from that. Again, I learn so that I can improve my knowledge. So, sir already told my life's journey, BTech and MTech, PhD, Kanpur, and then sometime we worked in other place. Mainly, our research activities are solar and wind power, power electronics and drives, wireless power transfer, smart grid, EV design, etc. So today, if you see that everybody, we all study about the microgrid, their integration, all control methodology, everything we work very nicely. And it is very lot of work is going on throughout the world about the microgrid. But if you see the microgrid design and planning, they are always different for different places. It cannot be same. For example, here at IIT Patna, so if I want to design a microgrid, first thing I have to see what are the challenges here to install a microgrid. For example, I one village is called Toipur village. So we visited there for installing a diesel generator and a solar microgrid. So we know that that is a open place. Children will come and play. What kind of microgrid structure you must design, and you put it so that it can be sustainable. And that part we generally never consider. We get some money, so we put a microgrid. After a few days, it is not working. Maybe controller is not working, the interfacing device is not working, or your some devices are failed, or inverter is not working. Some power electronics converters are not working. So there are a lot of challenges in the design of this microgrid planning. That is why this topic I bring, because after we design a solar plant for Port Blair Air Force Station, after that, we saw that we design in one way. After going there and installing it, everything, because it the sandy, it is a completely sand area. So how to develop a structural stability? That was the most important part there. Second part is after structural stability, the wind speed is very high. How to remove this sand particle from the wind? That is another challenge. That is why when we design the microgrid structure, generally when we do the hardware of that one, or you want to deployment that one, lot of challenges come, because you don't teach the local people how to operate. The local people, sometimes they think that the inverter is not working. They will bring a stick. They will put some bitting on the inverter. So they do not know. So they think that if we can hang or something vibrate this machine, it may work. So like that, there are a lot of challenges. So similarly, in the electrical power challenges, you see today, we are having aging infrastructure. Okay, long back we put it. And second one is a reliability issue. Reliability issue, I will tell one of the beautiful story that once I was traveling from Behra to Delhi in the near Ara, the overhead line, because of the cantilever beam in the train station, So it was always there is a friction, and the wire became very thin, and it became two parts, dismantled. So that is how the reliability is most essential. Then it is security comes into picture, because anyone can come and connect like there is a theft. Then market dynamics, various market dynamics means there are deregulations, market deregulations that must be taken care, and rate and pricing. So rate, what is the pricing, and different kind of distributed generations people are putting nowadays, without understanding. Like nowadays in India, we don't consider that road size. We just purchase a car. Like if you go to Singapore, in Singapore, the purchasing cost of the car is half of the road tool or the tax you have given for the using the roads. So that is why people prefer to travel in a public service. That is why there is a systematic number of vehicles that is increasing or it is decreasing according to planning of the government. Whereas in India, everybody purchase a car, they do not know how the road must be expanded according to number of cars comes into picture. So distributed generation need to allow the high grid. There are independent power producers, how that can be integrated, and efficiency optimization is another thing, that local generation and local utilization will solve that problem. Rising energy cost due to the rising in the oil price. Then there are conservation, because there is a limit in the source of energy. That is why you need to conserve. And mass electrification. Today, everywhere electrifying we do without any supply or demand analysis. That's why the concept of source control and the demand side management comes into picture. And renewable energy integration into the grid. And renewable energy integration gives a lot of challenges, actually. So green energy to reduce the carbon footprint. So the topology of a smart microgrid, when you see a network, it is interconnected network. If you see complete energy system, there are interconnected networks, they are connected, and some connections are the low power utilities, medium power utility, and high power utilities. So all this power, they are distributed according to requirement by the consumer or the customer's need. That is why this distributed network are very highly complex and is spread all over the place. So that is why it can connect or it can disconnect. For example, there is a co-generation power plant where all kind of renewable energy can be generated and locally it is utilized. For example, in IIT Patna, we have 1 megawatt, and each building we have 350 kilowatt of the power where it generates locally and used locally. And there is a networked intelligence that there must be, if there is some fault or there is a problem with the grid or problem with the inverter structure, that can be taken care by using different kind of the structural or the different kind of controller analysis. And the load profile are wide, actually, from industrial to residential to official loads are there. So that is why you must understand that what is the topology of microgrid structure. Especially when smartness comes, then you need to add all kind of sensor, meter, and servers. So what is the evolution of smart grid? There are different kind of microgrids, and these microgrid structures are called the distributed microgrid. And nowadays, few papers you will find that clustering of the microgrid. If there are n number of microgrid, how to reconnect all of them? That is another challenge, that one. Because the voltage and frequency control, the two are very, very important factor by which one can integrate with the grid. But you see, your old age or the conventional power grid, there are central generation somewhere, and then you have a transmission system, which is called the Power Grid Corporation of India in our India. Then it brings to a substation near the state control. For example, in Behra, Power Grid brings the power and supply to the state government, and state government have distribution network, and state government support to the distribution grid. And that then all the customers are connected. And in that place, how your microgrid will come, because already transmission system in India, they are transmitting power at peak power load. And only thing is that you can connect all these microgrid to the substations and the distribution network, so that locally generated power can be utilized by the customers. So this is what the total evolution takes place. And what evolution takes place in the smart grid? If you observe one thing, smart grid cannot be replaced by the existing grid. If you want that, oh, this grid connection is there, so let me quickly connect, or let me make it a smart, it is not possible, because all the grids are already connected to the system, different components in the system, and each system needs to be digitized. So when each system is not digitized, then it is very difficult to understand the concept. So then existing electricity grid can be entirely replaced by the smart grid. If each component of the grid, you can remove that component and put a smart device, then that can be enrich this grid structure. And the smart grid would and should coexist with the existing grid, like in a parallel line. Okay, sometimes you will find in the train when you are traveling, this side one grid, this side another grid. That is called the parallel grid. So that can be possible. So this is also another chance of that smart grid and the general grid, they must coexist together to enhancing its capability, functionalities, and capacity as it further develops. So then, research focus. What generally today we want to do, what kind of research? In the smart grid structure, the first thing is that the protection is the important thing. To have the protection, because in the smart grid, self-healing capability is one of the capability by which, like in your body, if there is a woundage or something scratch come, so what it happen? Automatically body manage that one and protect the body, and that is called the self-healing capability. Similarly, today also we want the power grid must be self-healing capability, and that is what protection, switching, dispatching the power, control and management, etc. should be taken care. That is in the operational issues. Then regulatory and standardization. You need to do regulatory action so that all the voltage, current, frequency, all should be maintained according to the standard component rating or by the standardization. Then third thing is your communication. That communicate this entire, the communication, messaging, data networking, automation. They are the interfacing device between man and machine. So this need to be, this is a measuring device, You can say this is the estimated device, or sometimes we call the human interfacing devices. So this microgrid required how to develop that approach of this microgrid. To develop this microgrid approach, first thing is that you must approach network based. For example, you have a one RL network. Now you connect another network in parallel. So easily you can find out what is the current rating, what is the voltage, everything you can find out. Loop current method, everything method you can find out. That is why network approach is very easy as compared to the physical layout approach. That is why network approach, we go for that. That is what the renewable energy storage control, and then the what is the management of energy produced, and what is the ancillary service that can be provided with this same energy. And another one, sensing, monitoring, and communication. That is also another the component of this one. And network approach allow researchers from diverse fields to work together to develop a solution. For example, here there was a project from Bose Tech, Singapore. So in that Singapore, I was also working, and Professor Jimson from computer science. So we three were working. So what I was doing, I was controlling. I was working on the control aspect, and Dr. Jimson was working the prediction aspect of this smart grid. And another professor was studying what kind of fault generate the blackout. So you can see these three components you can bring together. Like in a software industry, whatever you are developing, you don't know where it will be used. Only the project leader knows where it can be used. So everybody, they work together and they give the data or give the programming, whatever they want to give. And then all the things combined together, then they utilize it in the final research project. So that is why network approach are very good, because one component and one person can be assigned. So microgrid design process. First thing, what you need to design? First is benchmark completion, microgrid elements modeling. What are the elements required in that microgrid, and how to control those elements by using modeling and design. You must model the components, and then you can use a controller. And you have an information and communication technology which can give you the information or the display, or you can see that what is my utilization factor or how much power I have utilized today. Then we have a different the data requirement and specification. Then we have a design criteria. So what are the design criteria? There are voltage control, frequency control and protection, energy management, load management, and demand response. All these are the one component of the control aspect, a design aspect. Then testing and validation one can do. So what kind of microgrid structure you can design? For example, once I was in Pretoria University, near Pretoria University, if you go from Pretoria to Johannesburg, there is a place called Lipes. So in that Lipes village, that the Pretoria University, they wanted to give some power because it is a very remote village. So what they designed a solar system, and they gave this power to them. And you can see that this is the remote community, but you can provide the power to them without any big electrical line. You need not to draw this electrical system. Then there are also campus-wide microgrid. You can see the top view of a campus-wide microgrid where there are different kind of power supplies, but you can see that there are ample amount of solar energy which is integrated with the grid here. And then there are military base. And I remember last year we developed one project of 1 megawatt for the Port Blair Air Force Station. So they are a military base. So what are the first thing is the design. What are the benchmark? Whether you are designing for a rural area, whether you are designing for a campus or certain loads, and whether you are designing from a remote place, there are a different kind of development is required. For example, I remember I was working with one of in the General Electric Bangalore. That time I was posted in Hong Kong. So we used to develop the wind turbines and we used to fit to the local loads. So we used to design that wind turbine, and the wind turbine, they used to run and give the local load. When you give a remotely a wind turbine generation output to the local load, you will see that there are the frequency fluctuation rather than the voltage fluctuation. So how to stabilize this frequency fluctuation is one of the challenging factor till today in the remote area power supplies. So when you have because the rotor is rotating at a different speed according to the wind speed. So that rotor, they gives lot of vibration. The centrifugal unbalance takes place when the proper load and source is not managed properly. If your load is very high, it will give impact on the generator. Generator will give impact on the gears. Gears will give impact on the wind turbine. In that way, whole control or the centrifugal force became unbalanced in a wind turbine because of the secondary frequency control is not balanced, not properly controlled. And second one, microgrid element modeling. See what are the generators? For example, in Behra, the wind generation capability is very low. So that is why the wind, when you apply a project proposal, they will ask, it is not good to put proposal in the wind for the Behra, because Behra there is no wind. And then different kind of energy sources, solar, wind, fuel cell, hydrogen, whatever it may be. Then you have a loads, local loads. So what kind of load you are going to supply? And third one, local energy storage option. What kind of storage facilities are available? The second one is the modeling trade-off. Trade-off means taking care of the different structures and modeling analysis. When you design, for example, we design the controller for an induction motor drive, or you design a controller for a human, the biological system. If you see biological system, it is completely nonlinear. That when you design a system, you design a linear controller. That is why the trade-off is required during modeling, because exactly parameters you cannot find. Second one, exact modeling also you cannot do. For example, I will give one very beautiful example that long back I visited to Ahmedabad space station, and I met a scientist. I forgot what is Mr. Paul. So he was so expert in a matrix reduction that if anybody, they will derive the matrix equation. Nowadays, there are computer, MATLAB, you can do everything. That those period in 1995, that time they used to write in a paper and pen. So people will give 100 into 100 matrix, and this Dr. Paul will reduce that whole matrix 3 into 3 matrix. So it is, I asked, how do you reduce very quickly? He told, this based on our design, long back we are doing design, so I can understand which values are observable and controllable, and which values can, without that value, it will not lose the stability. That is why I choose those values. So beautifully he designed, and everybody will accept because it will work perfectly. So that is how the trade-off is sometimes is required. Then we design the control system and how to approach this control system. So we identify this something and we tried. For example, you want to control a DC link voltage control. So your control objective is to control the DC link voltage, and injected current should be in phase with the supply voltage or the grid voltage. So injected current must be unity power factor, so that you should not inject any reactive power into the grid. So that is how you need to design the control system. Second one, that when you design the control system, then you have to interface. So that is called the information and communication technology, by which you can integrate with the system, with the smartness or interfacing devices. Then combined power and ICT modeling. When you have a electronic or the communication and information, that must be combined with the power. And power and communication layer, there must be many power and communication layer. And then you study the system. When you get it, you can study the system, okay? Then you can study whether this will work for the grid connected or isolated system. And after that, this case study can be developed, and this study should go and operate. And you need to test this one by using real-time simulated. Today, different kind of hardware in loop simulators are available, and you can simulate the entire modeling with this one. And then once it is studied and perfectly you have got the result that no modification is required, then you can go for the planning or design step, okay? So that is why the design objectives are, must be more environmental friendly. Second one, it must be reliable. Third one, it must integrate the variable sources such as renewable energy sources without any problem, okay? And then cost reduction, there must be lower cost in the yielding as well as utilizing the energy. And then reduce the losses. Locally you generate, locally you use. There is no transmission loss in the line. And then you must have low loss so that the efficiency can be improved. And then improvement, that is about the energy dispatchability and flexibility. What do you mean by flexibility? Flexibility is like a rubber band. You take a rubber band and pull the rubber band. Again, you leave this. Rubber band will come to its original point. Similarly, in the power system, you have a thermal limit, you have a steady state limit, you have a damping limit, and all these limits are nothing but these are like a rubber band in a rubber system. You pull it, and it will come to, again, when you release it, it will come to the original point. That is called the flexibility in the transmission system. So there are different benchmarks which is defined by the SIGRE, That one is a campus type microgrid where you use in a specified campus network where the minimal number of generators and so the generators and the utilizers are there. A typical utility scale microgrid that little bigger community, and then we have a SIGRE microgrid, which we will see. First thing is a typical microgrid. You can see this is one of the typical microgrid. Okay, you can see there is a transformer of 3 into 500 kVA, and then there are loads, and there is another distribution transformer, and then you have a DC, the battery module, solar module, then electric vehicle module. And this is a small microgrid, but it is not only these are the components. There are many components also there. So this is a typical campus microgrid where the smart home system and every device in the home are connected with the different smart device to the Wi-Fi and other communicating devices, and information of each device you are getting at your substation or the utility office. You can get all this information, and then you can sometimes program all these components, and that program will work. There are solar, wind, or there are also utility scale, the power system where there are grid connected also, that is possible. So the utility scale, this microgrid structure are, this is, you can see a small hydrocubic, they have developed this microgrid structure. You can see it is 28 MVA and star delta substation transformer. And this is, you can see that there is a tie line, okay, which is moves around this microgrid. And this is the utility scale microgrid. You can see here, there are diesel generators, and there are the energy storage element and wind power also. And there are also generators. You can see 400 kVA diesel generators and induction generators. And there are also a controller, okay, microgrid control center, where you control everything, reconnecting, connecting the device in different systems. So these are the SIGRE microgrid. You can see here, this is the SIGRE microgrid. It is flexible, very flexible for modeling as a mesh structure or radial structure. Anything you can see, you can do this microgrid structure. And this is the medium voltage and low voltage transformers are utilized here. And there are 3-phase main lines, and there are also single phase. Means this is combined of the 3-phase and single phase. You can see where the 3 marks are there here. There are marking and the 3 that are the 3-phase line, which is not marked, that is single phase network. Okay, so where 3 lines are there, that is a 3-phase network. So this network you can make a ring main or you can make a radial system. There is no problem in this one. So that is why this required how to recommend this type of this. That is why modeling is one of the important structure. Then studying this one. So if you have this. So when we have this distributed energy sources, there are PVs and there are synchronous generators and there are some kind of storage element, and all these things are connected And you can see that energy management, voltage control, frequency control, transient stability, economic feasibility, vehicle to grid, then sizing, all these power quality study are requirement factor. You can see where we should design this one. So when you see a microgrid elements and modeling, so if you see, there are two generic load models. If you study, and there are two generic load models. One is to study the steady state. Second one to study the dynamic behavior of the different loads. So a current source based model, or you can say that the impedance model of the system is there where you can study the both steady state and dynamic condition. And second one, a grid connected inverter as a active power and a reactive power as a reference you must feed in the control structure. So we will see that how the reference active power and reactive power. So what do you mean by active and reactive power? I told you the active power is the useful power which you draw from the grid. And reactive power is another name of reactive power is the carrier power. For example, I will give one example of active power and reactive power. First active power is that when you want to transmit the active power, like a newborn baby, when the nurse brings to you, she brings the baby along with a lot of cloth or warmer like that. She brings and gives. The warmer or cloth is not the main, is not main component. Main component of that that baby is the main component. And the cover or the warmer is the carrier of the baby. Similarly, the reactive power is the carrier of the active power in a transmission system. So that is the way how to create that one. There are different ways. That is why first is current source modeling. The current source modeling, why we give this, there are voltage source modeling and current source modeling. So generally current source modeling, we give all kind of, because generally our loads are inductive in nature. So inductive in nature, so equivalent to become a current source is became most fitted thing in a network system. Then you have a PLL structure and you convert the ABC to alpha DQ component from the ABC to alpha beta to DQ. So what the DQ component, they controls the complete in the structure of the grid. And then there are also another component which we model, and we will see in detail in the same course. Here we are going to do the detailed things in this one. So grid tie inverter, you can see here, there is a DC link voltage, then there is an inverter and filters. They are through the isolation transformer or sometimes step-up transformer we also use, and connected to point of common configuration, point of common coupling, where your loads are connected, all the loads are connected there, or it is connected with the main grid. So if you see this configuration, grid tie configuration, the control structure, if you look at this is a control structure that it can be used for different kind of controllable loads also. So for example, sometime we take IQ as the DC link voltage control and IG as a, or ID reference and IQ reference. So these are the DQ axis component, and sometimes we take this IQ and ID. Why that IQ ID is required? Because this, by controlling IQ and ID, you can inject the power to the grid at a certain angle difference level. For example, you want to make it leading, so Q reference must be negative. If you want to make leading, Q reference must be positive. And I am not telling that if it is negative, it is lagging, and positive, it is lagging. No, it is depend on your convention, what you take into consideration. Okay, then from here you have developed the controller, then DQ to ABC we have converted, that will control the inverter of the system. And I have not given here the inverter converter controls, but in the later section we will study. Starting from a small device rating, we will go very, very high rating. So then it comes to the information and communication layer, where you can see that all this data need to be processed and analyzed, or it may be stored for the future identification purpose, or future we can utilize those things. And then there are physical models. And there are different kind of the structure of or the communication structure, like house area network, local area network, and wide area network. So these networks depend on the what kind of service you want to take care. For example, in your house, you want to use the IoT-based monitoring unit. So what you can utilize that? You can see your current, or you can see the voltage. So in general, house loads are stable. But when you will go for a big transmission system and distribution system, there you just put your things, you will see that what is the challenge. So that is why, according to requirement, we choose whether it is a home area network, or it is a wide area network, or it is a local area network. So what are the system requirement? First thing, that you must see that you have a network model for microgrid design, and you planned also. And then according to planning, you design what is the bus bar data, circuit breaker data, transformer, generation, cable, then load data, utility protection data, and energy storage data. All these things comes under the network model. And then you have a grounding interconnection transformers, and then this network model you give for the different operating range, and after that determine the parameter. Then you can have a load study model, load flow study model or analysis. Then short circuit analysis you can carry out. Then what are the data or specific requirements are there, you can taken care of that, the planning condition of this microgrid. So what are the planning? First thing, actually. First thing is the community microgrid are required, they are increasing in power. So today, for example, in IIT Patna, we have actually load are around 2.5, less than 2 MVA. Less than 2 MVA load, but we put 2 and 2.5 MVA, 2.5 MVA. Why that we put the 2.25 MVA? Because when this will grow, it will grow, then you require all these things. So as the campus will grow, number of houses increase, everything grows, the power supply or power taken from the grid also grow. That is why you need 2 transformers. Now from 1 transformer we are supplying. Now in the future we will have 2 transformers. So that is why the dynamically they are increasing the power requirement. So when do we design that one? What kind of microgrid design we do? First thing is a robust commercial software by which you can model the system. Okay. And today, the cost of this, there are a lot of cost in this one. And that is why these microgrids need to be properly designed. And the software cost is very high. And when you design, it is vendor-specific libraries you must create. And you must design from the low level to a library element you must develop, that one. Then you need to the high level of automation. There is lack of high level of automation and lack of scheduling optimization specific to microgrids. That is why in this one of the projects we also got on this one and the imprint design the software tool for the microgrid planning. So this is to build the component library. First thing, if you in a MATLAB simulating, you take a component because you do not know what is inside. After taking that component, you are seeing that it is not working. So that is why it is very important to understand the library and develop the library. And then microgrid should be designed, and after that it must be tested. So how the workflow? First thing is specify design specific. Design a microgrid, then you specify what is the capacity load and what is the peak load and what are the renewable energy you can utilize there. For example, in Behra, there is no wind power. So how the wind power can be supplied here? So that is also another problem. So what kind of renewable specification you must give? Then the library of discrete event model for microgrid component. Then automated, it will generate different kind of component and then they will generate a layout of microgrid. Okay, this is our work that once you feed the capacity, peak load demand, renewable energies, it will give you a layout by which again you can simulate and you do the permutation combination and you reduce the number of components that you can do. After that, test, if you tested okay, then you go for test-based validation. That is why the component-wise verticals are the front end and initial the specific environment. Okay. First is to develop the component library, then generation microgrid model, and then development of microgrid library, and then optimization for the power and reliable design of the microgrid, then designing the complete hardware of this microgrid. So if you see here, the testing component is done at IIT Kharagpur because this project is based on 3 people. So they do the IIT Kharagpur, and those test beds is developed here at IIT Patna. So that can validate by using the hardware component into this one. Then you can see the open Modelica microgrid structure which they developed here. And then there are a lot of algorithms need to be developed. If you see here, this is a microgrid model, and what are the number of AC feeders, loads, and distributed energy resources. Then the component library, you collect the component, you interface with the grid, and then building interface, then the logic will, this will work. And now you see this is the component library. From that library, you take all the components like transmission line, rectifiers, batteries, wind power plant, load, etc. Everything you must plan here. And then you have a sample design, and you 1 or 2 you can design. And this is how you can develop this complete microgrid structure. Okay, so that is why here in this one it is given that one must design the microgrid structure and must this microgrid structure must give according to your load requirement. So then we have developed a simple hardware model, and let me go through that hardware design of the smart microgrid system. So here, this is a microgrid system. We have a solar, wind, and you have a storage. Then you have a DC utilities and AC utilities. Okay. After this microgrid, you see here, the renewable energy is very, very abundantly available energy, and the bidirectional converter also used to charge and discharge of the battery. And then the microgrid should have capable of operating both grid connected and islanding mode. Okay. Then that need to be properly controlled, the intermediate condition of the power, and that needs to be controlled, and then operation and control. Then how to design the hybrid DER system, okay, or the sizing of this one. So this can be investigated here. This is a proposed microgrid. You can see there are red color boxes. These red color boxes are called the smart switches, okay, or the smart meter, okay. So each after solar panel, there is a smart meter, and after the single phase AC grid, before the transformer, there is a smart meter, and all the loads, there are smart meters, and this in the storage or the wind power also, there is a smart meter. And this smart meter properly, this is a model, and I'm not going in detail. And this modeling, you can look at our paper, which we published 2 years back. So then, this we design a proportional and resonant controller, and this is the structure of that resonant ampere controller. And then complete closed loop controller we design for study this for the stability of the system. And this is our experimental validation. So you can see from here we have a solar power coming through this inverter and feeding to this transmission line. If you see here, this is your transmission line. The transmission line is that you can see that each component of the transmission line represents 80 kilometer length. And you can see that the output is here in our DSO. So we get power from the inverter single phase and give this power to the transmission line. And the transformation lines are represented or designed for 80 kilometer, 160 kilometer, and 240 kilometer. So these are designed, and this is actually connected with this system. And these are the smart single phase IoT based energy meter, and these are the smart switch and smart information system. And these are the few results. You can see that both the current and voltage are in same phase, and this is the performance. This is grid voltage performance. You can see this is showing you like a this is showing like a PWM signal. Okay, that you can see here. Then this is the dynamic loading condition. When the loading is dynamic, then this loading can be performed for different kind of dynamic load. So this is what the smart microgrid, and smart transmission system and penetrating into grid is another aspect. So the short transmission line is less than 80 kilometers. medium transmission line is less than 240 kilometer, and long transmission line is greater than 240 kilometer. So if you see here, this transmission system, we want now to transmit this the power from all these type of transmission system, and these transmission system are built based on this energy management system of this transmission system. So the smart meters, there are also a lot of advantages, and this is the modeling of the transmission system. And after modeling, you can see here, this is the transmission system. How you can test? So this transmission system, you can see these black color small box. They are called the capacitors. Okay, the stray capacitors or the line capacitance. And these below is our inductor. You can see here, below is our inductor, and they are treated as a smart transmission system. So when this will behave like a long transmission system, medium transmission system, and also short transmission system. So when you have the long transmission system, what effect you will get? When the load is lightly loaded, then there will be a current effect and the in the receiving end. So that effect we have already studied here. And then you have a smart devices where you can get all the information here. Okay. Now, this is our energy meter data. You can see that what time they have. Now, this project is one of the best imprint project, and we got also one of the Grid Tech Award. So let me show you one video, which will be, I will stop this one, and I will show a video where you can appreciate how actually this smart transmission system was designed. So just a minute. This is okay. So hope everybody could able to see my screen, and just let me open this. Okay. So this is our transmission system, the transmission line where you can so this is the Okay. So this is one of the system design which we have designed for the this one for the transmission system. And there are many such things we have designed here in the here is this. So then we will see this low cost. Now we will take a very small system. Like with this one, we developed for one village called Toipur village in Bihar. Okay. So we developed the cyber physical control. Like you have a sensor, you have a rotor, and you have some kind of renewable sources, and they are connected with the through the data from the sensor. They are given information to the grid. So this complete layout design, I am not going. We design a nanogrid system. Microgrid means you know that it must be the power more than 10 kilowatt, and the nanogrid is lower than that one for one house, and bidirectional charger. The system here we study very small system, that we have a PV and the internet connection and a user and a battery charger, bidirectional converter. When we have the how you can design the cyber physical energy system modeling, you have a routers and you have a different distributed generators and you have a sensors. So all this data must be processed through the single channel. So this PV modeling, we are not going in detail of the PV modeling. Okay. So this is the PV modeling. I think every one of us will know this PV modeling. So we took a solar panel of 36 number of solar cells in series configuration, and this is the solar panel power or the specification. Then we designed a multi-input, multi-output system where both the controller and this can be properly coordinated and control this. And this is the model of the communication system. There are NC number of controllers, and NF is the number of sensors, NR the number of relays. And they all are coming together, and how to find out. Here, there are a lot of things you can do, actually. In a research, you can study how the control affected different due to the different sensor data. That is also another challenging problem. So how the controller output coordinate the relay nodes, actually, that is another kind of research one can do. Which sensor will give information first? That is also another. First, you must know that egg first or hen first. So which one is a very difficult problem. Then sensor coordination. What are the serially sensor data you can get? And what is the frequency of the data to get the better? So there are a lot, n number of research problems are there. If anybody wants, they can do a lot of research on this area. That is a very new area, and very lot of people, they are also confused in this area. So anyway, so where all this data can analyze, then we design an online solar portal, system portal. Online means wherever you put your device, you can get all the data by standing here at IIT Patna. So this is how you can see the remotely you can control the solar panel, you can control the battery, you can control the port 1, means load 1, you can control load 2. Just by clicking on this load, automatically it will switch off the load. By clicking on this, automatically it will disconnect your battery. So there are a lot of things you can do. And you can see here what are the voltage, what is the current in this live current data. You will get lively that it is monitored. It is online monitor portal, monitoring portal. So first thing, we designed a home area network where we have a fan and light load, and it is supplied by a solar panel. Because generally in the household we have a one fan, two light we generally provide. This is what the experimental setup. And you can see here, sometimes when the daytime, when the no grid current is supplied, all the current come from the solar, and it is fed to the load. And few current is charged, nearly 10% of the current we charge the batteries if there is any storage element in our battery system. And this is also when you are charging and discharging this DC link voltage, that is also, it is given in this one. You can see here the current. And you can see here when it is going from charging mode to discharging mode. This blue color shows you from the charging mode to discharging mode. And that way it controls this complete control. And there are many references. And I will tell you few microgrid which we install. First microgrid we install at IIT Patna. So long back, when I was working in Tennessee, we installed this microgrid system. And this microgrid was 12 kilowatt, and there was no wind clearance, no optimal angle for the summer and winter, no structural stability. So this wind and this control, this was not for a long time it was working. And then there are smart microgrid project, another project we did at Schneider Electric, which is near to Nashville. Okay, it is near Nashville, this project, and that project is around 1 megawatt project. And this is our AC/DC microgrid structural design. We designed this whole microgrid from the scratch, and this whole microgrid was designed, and there is a wind clearance up to 200 kilometers per hour. So you can see that this design is very perfect. And then you see here, this is our control room. This control room, the solar grounding must be separate ground. So you should never connect the solar ground with the building ground. As you connect the building ground, most of the time, the solar, as soon as you touch the solar plate, there will be heavy spark or there will be heavy the current, because that will create that floating ground. That is why grounding must be very perfect. And this is 1 megawatt solar plant at IIT Patna, where we have installed 1 megawatt distributed solar energy. Then another we developed 40 units of 1.2 kilowatt solar plant and supplied in the Araria district of Behra. And this is another solar plant we installed in the Toypur village for the 50 houses, and completely battery storage, and it is the generator supported solar energy system. And this system, we have a variable DG system. There 50 householders are supplied here. And our last project we did is the Port Blair Air Force Station, where we have installed 1 megawatt. There was a lot of challenges, but the challenges are taken place. This is the layout of the Air Force Station at the Port Blair. These are the layout of the solar panel. And this is the layout of the cabling. So how all these cables are connected. And this is the layout for the earthing pit. you can see there are so many earthing pits. Nearly we have given 5 earthing pits at the solar plant, and nearly because the complete area is sandy, only sand particles. That is why we give this lot of earthing, so that if one earthing fails, other earthing will work. And then we have another solar wind project here at IIT Patna from the Ministry of IT. We developed here in the Teaching and Learning Center. Anybody is interested to do any hardware, you are most welcome to this place. And this is the design planning tool. You can see there was a horizontal axis wind turbine and a vertical axis wind turbine and a solar tree. The three are connected together. So you can see here there is a wind turbine, and here it is a solar, and this is the controller connected to the smart load in our garden. We have supplied to this smart load. If you see here, I will share another video I will show you. So I can stop here and sharing this video. So how we install this complete setup, you can see here. So there was a horizontal axis wind turbine and a vertical axis wind turbine. Vertical axis wind turbine work in the low speed operation, and horizontal axis wind turbine work in high speed wind. So these are the loads are connected. So we have a wind and solar integration together connecting to this load. There are also a few projects we implemented, and this is the final project which we implemented. So I can show this video and stop here. If you have any question or comment, you can.
So thank you, sir. Any queries
Okay.
from participants?
Okay, thank you very much.
Any queries from participants? Any queries? Sir, I think no queries, sir. They have understood very well.
Okay. So I will give my email address, so anybody has any query, they can mail.
Okay, sir. Thank you, sir. Thank you very much, sir, for your very valuable and lecture. And you have given research directions also, sir, in smart grid. Those who are working on smart grid, definitely this is very helpful for them. Thank you very much, sir.
Thank you very much. Actually, you should have told me what is the time. I forgot that. Is it?
Time of up to 4, sir.
Oh. Okay.
Okay.
Then thank you
sir.
very much. Yeah?
Thank you, sir. Thank you very much, sir. So thank you very much all. So tomorrow first session will start at 10 o'clock. So please join at least 5 minutes before starting of this session. Thank you.